So now we're going to look at sample 2, which we recognize has a slightly different sort of look to it. Our first input is at 2 this time instead of 0, and we see that the values are decreasing instead of increasing. But we can also tell right away that it's definitely not a linear function because the numbers are not decreasing by a constant difference or constant amount. They are indeed changing by a constant ratio. So we first need to figure out what that ratio is for these values. So the first thing I'm going to ask myself is 256 times what number is 128? Now, you could get a calculator out and do this, but I'm going to show you a quick spreadsheet trick in case you're curious. If you type an equal sign, that tells the spreadsheet I'm going to make you do some kind of math. I want to know what 128 divided by 256 is. So H7 refers to the cell number that the 128 is in, and the 256 is in H6. And if I hit enter, it tells us that's 0.5 or a half, which means that 256 times 1/2 is 128, which is true. Now I can keep repeating this and dividing and making sure that they're all a half, but this other cool spreadsheet trick is if you click a cell, there's this little box in the corner that shows up, and if we drag it, it basically copies the formula we've typed in, the division of those two numbers. So let's do that. And we see that the ratio is 0.5 for all of them. You can click on any individual cell and it will show you how it's computing the value. So in here, in this cell right here, it's saying we're doing 32, which is H9, divided by 64, which is in cell H3. So we have this common ratio of a half. Now there's two different ways we could approach writing the formula. We don't have the y-intercept or the value when x is 0 this time because the table started at 2. So one strategy we could use is we could insert some rows, or you could move the cells down. So I'm actually going to insert a row above, and I'm going to insert another row above, and I'm going to work backwards to find what the term would have been when we got 0 as our x value. So we know that the ratio from the output times 0.5 gets us our next term. So if we want to work backwards, instead of multiplying by 0.5, we're going to divide by 0.5. Now, I don't know about you, I don't love division by decimal, so dividing by a half, or 0.5, is the same thing as multiplying by 2. So this number above 256 should be whatever 256 times 2 is equal to, which is 512. And the number above that should be equal to whatever 512 is times 2. And you can now confirm that this matches the pattern for this function. 1024 times a half is 512. 512 times a half is 256. So now that we've done that, again, we have f of x this time is a times b to the x. And in this case, our a value we found to be, when the input was 0, is 1024. Our b value, or our ratio, is 0.5 to the x. So that would be our equation for this exponential function given our second table. But this is another way to write the function formula. So we would love it if the table started from 0. So I'm actually going to create a new column, which I'll color code in a different color red, and I'm going to call that x minus 2. So what I'm going to do is I'm going to take the input value and I'm going to subtract 2 from it. So for example, if x is 2, 2 minus 2 is 0, 3 minus 2 is 1, 4 minus 2 is 2, and I think we see that the pattern should still be that each x minus 2 value increases by 1. Well, the output when x minus 2 is 0 is 256. So remember, we have f of x equals a times b to the x. And what we could see here is that our a value when x minus 2 is equal to 0 is 256. Our b value, our ratio, is still 0.5. The only thing that is changing is instead of our variable being our input of x, our variable is now x minus 2. So if we raise this to the x minus 2 power, we would get a function formula. Now, you might not be convinced that this is the same as what we got using our other method, which, if you remember, was 1024 times 0.5 to the x. So sometimes I find when I'm not convinced about something, I love to go and just graph it instead. So what we can do is go to Desmos, graph it, and see what we see if they're the same. So now that we're over here in Desmos, I can type in our first function, which was 1024 times 0.5 to the x. And I can't really see it that well, so I can always, shift the graph over. I would love to be able to see the y-intercept. So what I'm going to do is I'm going to change my y-axis to be from about 20 to about 1050. And now I have a much better view of that graph. The other function we just found was 256 times 0.5 to the x minus 2. Put that in parentheses. And what we can see is that with both of them graphed, no matter how close I zoom in, they are indeed the exact same graph because they are completely on top of each other. So those are both valid function formulas, and you are more than welcome to do whatever one works best for you.